Good morning, everyone. Thanks for coming to this Immersive Analytics Toolkit tutorial. So my name is Maxime Corday. I'm from Monash University, and I will be presenting our tool with Tim Dwyer, also from Monash, and Andrew Cunningham from University of South Australia, which is kind of a collaboration project. So basically what you'll see today and learn a little bit is how to build immersive data visualization and interactive immersive data visualization within the Unity editor. So using like simple click menus and just like simple interface interactions. So you'll learn how to build like scatter plots, bar charts, trajectories, visualization, animate all that, put all that in a 3D environment and interact with it. The aim of this tutorial is to first really try and understand what are the current research challenges in this topic. So we will start with a presentation of some of our projects in immersive analytics. Then also, it's going to be a kind of a technical workshop at some point, and so you'll get to know some important information on immersive visualization development. And finally, well, you learn like the core of this tutorial is to learn the I8K tool, so the immersive analytic tool. So first of all, we'll have a very non-programmatic approach to seeing how we can like from a CSV data source, from a data source, create a immersive data visualization environment, just using like the editor, the Unity editor, and then at the end of this tutorial, we'll show you how to do a bit more customized visualization by scripting your immersive visualization with the core API of our tool. So just a bit of instructions here. So the format of this tutorial is going to be fairly interactive. So we're going to do some live coding, live demos and stuff. But if you want to follow, but I assume no one has their own virtual reality headset, but you can download those tools. So we advertised a couple of weeks ago. So yeah, if you wanna get the I8K, you can just jump on the GitHub, and then you need there are instructions on the GitHub as well with a direct link to the right Unity installer. So for now, we're just handling Unity in 2017, but we're actually porting the code to Unity 2018, and it's almost there. Also, if you happen to have your VR gear, also please download VRTK. So all the instructions are on the GitHub. And the very last disclaimer: if you have a Mac, well, just use Boot Camp and Windows, because we use a lot of the graphics capabilities of the computer, and so the drivers of Mac don't really handle all the shader codes and everything that we have developed for our tool. Okay, so this is just a quick overview of our tutorial. We first have a team who's going to introduce the field of immersive analytics research. Then Andrew will introduce, we'll give a Unity overview. So we'll learn, we're going to try and do a very crash course, like of a 30 minutes crash course on how to use Unity efficiently for I8K, but Unity efficiently in general. Then we'll have a more hands-on the I8K session, and that's going to last a little while, but there will be a coffee break in between. And also, yeah, during the coffee break, we have another virtual reality setup here. So if you want to try some of the tools that we've built, yeah, you're most welcome to come and have a look. And in the last section of the tutorial, we will do some activities, and you will probably code if you want to, or you can just download the solutions on the GitHub and just have a look at the code. Yeah, and again, at the end, if we have a bit of time left, we'll do a bit more demos.
Good morning. Yeah, this talk, this little introduction is really just talk. So please use the opportunity to download Unity and get ready to do the practical part. We started talking about this thing, immersive analytics, in about 2014 at Monash. It came about because we were lucky enough to have access to this Cave 2 facility at the Clayton campus of Monash in Australia. It's a large surround screen with 80 megapixels, 80 screens, cluster rendered with each column of 4 screens is its own computer. And as you can see, it's very useful for things like giving tours. That's our former dean showing off the Cave 2 to a bunch of people in suits. We also did our best to use it as a visualization environment. So that's our colleagues there visualizing metabolic pathways and biological pathways on the wall of the Cave 2, treating it just like a big display wall. There's some art in the bottom left-hand corner being displayed. Over in the bottom right there is a new facility that we recently opened, which we're calling the Future Control Room, and it's set up like the kind of control room you might find in a power grid operator or an energy market operator. And there's another big display wall, but also these workstations. So it's intended to be a very practical environment for simulating those kind of energy market management operations. However, so this is kind of the future of visualization as it was seen up until about 5-10 years ago, and certainly it was the vision of visualization for a long time before that. I put it to you, however, that this is not really the future of visualization. The future of visualization is something a lot more like this. So the Cave 2 facility cost about $2 million at a time when the Australian dollar was worth about the same as the US dollar. And by contrast, these new HMD head-mounted display devices, they cost, what, about 500 bucks? It's a bit more than that. You have to also plug it into a decent computer, but it's, as you can see, several orders of magnitude cheaper than a Cave. And as a visualization facility goes, it's actually not too bad. Obviously, there's not as many pixels, but it has this property that you can walk closer to the thing you want to see in more detail. It's not a these particular VR headsets are not pass-through displays, so the Cave has the advantage that you can see your colleagues that you're working with, so perhaps there's some advantages for collaboration there. But as we'll see, you can also use these for collaboration. And they also have these fantastic tracked controllers, which means that you can do very natural gesture interaction. Whether or not you believe in 3D visualization, it kind of doesn't matter. You can have with these things a display wall as large as the Cave any way you like. And the thing that is really exciting, to me at least, and for many others, is the idea of augmented reality. So not just virtual reality where it completely blocks out the world, but augmented reality where the headsets are transparent and you can see the world around you. So you can do immersive visualization wherever you are, out in the world. If you're on the factory floor, if you're packing shelves in a supermarket, if you're a surgeon in the middle of an operation, you can, using hands-free gestures, start interacting with data in ways that you would have had to go to a terminal to do previously. So that's really exciting, and I think has the potential to bring visualization into many, many more fields of use than it has previously. Okay, so these are all things we started discussing back in 2014, and we, I believe, were the first people to mash these two words together, immersive and analytics. We're quite proud of that achievement. But it's not just a buzzword. We put a lot of thought into it, and over time started to realize that it is a new way of thinking about visualization. And whereas visualization over the last couple of decades has become very much entrenched in laptops or desktop computing with a mouse and a screen that has fixed dimensions in front of you, immersive analytics has the potential to change the paradigm somewhat. So we see 3 goals for immersive analytics. Firstly, to remove barriers between people, their data, and the tools they use for analysis, to support data understanding and decision-making everywhere and by everyone. So you know, there's this democratizing aspect to it where it potentially brings visualization out of expert visualization centers or the offices of statisticians and to regular people in their lives. And finally, we want to make embodied tools that are intuitive, engaging, and make the best possible use of all sensory channels. So we'll talk a fair bit more about embodiment in a little while, but it's another really quite paradigm-changing aspect of immersive analytics, the idea that you can embody data in objects in the world around you. I'm very happy to announce that finally, after several years of work and contributions from a large number of people in our community, this book is now available, titled Immersive Analytics. It has many great chapters that explore wonderful themes about collaboration and interaction, and also set out the goals of immersive analytics. This effort was really led by Kim Marriott, who's sitting here in the front row, who's the first editor. Thank you, Kim, but there's lots of other people in the room I see here who were contributors. So thank you very, very much to everybody involved. This is available for download right now, so you can Google Immersive Analytics and Springer, and you can have a copy in front of you in just seconds. By way of a bit more introduction, I will just briefly do a bit of an advertisement for the immersive analytics research that's been happening at our university at Monash and also at Andrews University in South Australia. So we collaborate very closely with Andrew and Bruce Thomas from UniSA. And as I said, we've been working on immersive analytics for several years. One of the early studies was trying to make the best use of this Cave 2 environment that we were the lucky recipients of. So we were, as I said earlier, our first attempt was we were really quite skeptical about 3D visualization and stereo, and so we really just treated it like a big display wall. We did a bunch of stuff looking at how you can collaborate with these kind of big display walls. Unfortunately, it didn't come with touch. That would have been nice. So we looked at all sorts of alternative natural motion tracked gestures, interaction for visualization. And ways to share visualizations across different facilities and sites, doing collaborative visualization with other Cave 2 facilities. But not everybody has a Cave 2, unfortunately. And so, as I said before, the opportunity that we really saw for immersive analytics was these low-cost headset devices that really everybody can own relatively cheaply. So, in order to keep our dean off our backs a bit, we decided to do a comparison between collaborative visualization in the Cave 2 and the Oculus Rift DevKit 2, which was the state-of-the-art at the time. This was, what, 2015? So just a side-by-side comparison of these two environments. So at the time, the DK2 was, the field of tracking was really only a couple of meters, so you had to use it seated. By contrast, the Cave 2 is about a 10 meter diameter space, so there's enough room to move around a bit. The Oculus Rift, so you have to use it seated, but it does have tracking. You can lean, you can rotate. So we put people on swivel chairs. One advantage of the Rift is that it has a 360-degree field of regard, whereas the Cave has a door, which takes 30 degrees of your arc. However, as I said, the Cave 2 is much higher resolution, but you can get closer to things in the Rift to see them in higher resolution. Big advantage of the Cave is that you can see people. The polarized glasses are transparent, and you can see the people you're collaborating with directly, whereas the Rift is a shut-out VR. Oh, and the other big difference is that only one person in the Cave is head-tracked, whereas in the Rift, both people are head-tracked, which is really important. So you can't see the other participant when you're collaborating with them in VR. We did our best to give some presence to your collaborator so that you got an indication of what they were doing. You could see their finger, which was tracked with a Leap motion controller, and you could see their view frustum. We rendered a view frustum to give you an indication of what your partner was looking at. Yeah, but as you can see here in the Cave, only one person has the glasses with the tracking markers on it. So only one person gets the stereo rendered at the correct perspective. And that person's free to bob up and down, but the other person doesn't have quite the same. Okay, so we ran a big study, controlled study, getting people to solve network visualization tasks, basic shortest path tasks and pattern finding tasks in both environments. We tried to keep all things as equal as possible. In both cases, the network was rendered in a sort of horseshoe shape around the participants. And this is what we saw. So what's this? This is the cave 2. In the cave 2, looking at the movements of people from above, so we recorded, we're tracking their position the whole time, we recorded their head position precisely. You see that the two participants tend to follow each other around quite precisely. And so, well, actually, I guess what's happening is that the person who is not head tracked is following the person who is head tracked in order to get the correct perspective. And we see that only one person is really moving up and down vertically. The other person stands fairly static. And as you'd expect, it's the head tracked person who's moving a lot more than the unhead tracked person. By contrast, in the headsets, both people move fairly independently, well, completely independently. Which gave them, when we looked closely at it, we saw that they were using different strategies to solve the problem. They were able to divide and conquer more effectively, and there was a significant difference then in the completion times for the tasks that we're testing. So that was a really affirming result that indeed headsets offer a new degree of freedom than we've had before for immersive visualization. Okay, I'll pass over to Maxime now, who's going to say a few words about a bit more research we did at Monash.
Okay, thanks Tim for the introduction. So now I'm just going to show a bit more projects that kind of led to this Immersive Analytics Toolkit project. So yeah, as Tim said, we started exploring this back in 2014 and 15. And so yeah, rapidly we were interested in visual analytics tasks and so on. So really so to evaluate, like to port like visual analytics on a different environment, we started exploring several facets of the visualization research. So one interesting path that we have explored, and there are some of our collaborators on this project, is what we call spatial data coordination. So okay, so when you buy an Oculus Rift or a Vive, the default setup that you get is a head-mounted display and tracked controllers. And so by default, the way that you want to interact with your data is you kind of like project your data in the 3D environment in front of you, and you want to kind of interact directly with the immersive visualization. So we kind of reflected on this framework, and we explored what we call the spatial data coordination, which is the mapping between where the action happens and what you see on the display. So a very naive first spatial data coordination for a visualization task is to select, for example, the red cluster in that scatter plot. So yeah, a very first approach that we thought, that everybody has thought, is okay, let's just track our controllers, and then let's just move like widgets or just select the box directly, and yeah, we managed to select the data points. Problem though is, like, if you have a fairly big scatter plot or a fairly big visualization, you need to walk around, you need to do big arm gestures and things like this. Okay, so sit back and we think, okay, maybe we don't need to do all those like very big movements, and maybe we can have just like an embodied representation of the space in a touch cube that will just allow us to manipulate our data visualization a bit as a data cube, and yeah, we could perform like selection with like very tiny movements on touch faces. So yeah, we designed this touch cube, which is just basically a few touchpads from laptops stuck on plastic covers, and then we put a gyroscope in it. We wrote a driver, we hooked that up to Unity, And we plug that into a HoloLens, and we're like, okay, we are in a very different spatial data coordinated environment. Now I'm visualizing, my visualization is on my desktop, and I can navigate my 3D scatter plot and perform my selection, my visualization tasks, just with my tiny prop in my hand. Then we kept exploring, and this idea of like using the physicalization, like the physical affordance of the world was, of the physical environment, were very important for us, because we kind of, by exploring, we understand that, okay, some interactions has to be precise. So in information visualization, for example, when you want to do per axis selection, you want to select precise values on an axis. So we explored a different design, and we created this fader axis, which is basically an embodiment of the 3 dimension of the space, with on each axis of this device, we have actuated faders from audio and audio engineering tables, and so they can move. You can like actuate them and select precise values, and you get like physical guidance and so forth and so forth. Here is how it looks like. So now the the cube is aligned with the visualization, and we can perform the same, like per axis selection, but much more precisely, and it just gives us a different way to explore the data visualization. We stopped building devices at some point, and we started reflecting about the design space, and we really asked ourselves, what's kind of the design space of interacting with these immersive visualizations? So we came up with a 7-dimensional design space. The first dimension was the size of the interaction space. Yeah, where is the action happening? Am I sitting at my desk? Do I just need a small device to access and do my visual analytic tasks? Or am I in a big room collaborating with a lot of people where I want to be able to walk to somebody else to point at something, you know? So then another interesting axis is the degree of physicality that I want to leverage from my environment. So it's kind of a spectrum. Each dimension is a continuous axis. So on one end, we have a fully virtual environment with no physical affordances, except maybe for mouse clicks and things like this. And then at the other end of the spectrum, we have the fully physicalized, actuated visualization. And there is a workshop just next door to us who is talking about that at the moment. Then we had 2 more. I won't detail those 2 ones, but then, hey, how do we support navigation? How do we move around in our immersive visualization? How do we access like meta information? How do we trigger menus and actions? Another very important one is the display space. Where is my information displayed? Is it like stuck on my screen, or is it on a physical, in the physical environment, or beyond in a 3D immersive environment where I can teleport and so forth and so forth. And yeah, so the final dimension, which is kind of really probably one of the most important in this framework, is the mapping of the interaction between where is the input performed and where is the output. So you have like a very indirect, like desktop style input-output setup where you have like the mouse that is far away from the screen, and you just move your mouse and you click and you see the feedback happening. And at the very end, you have like a fully embodied, completely integrated visualization that you can manipulate. You can grab directly bits of the visualization. Okay, so that was just a first like reflection on this. How do we interact with the visualization? So the immersive visualization. So we kind of created that those devices that we were able to explain with our framework. Now I'm just gonna. So we kept going, and we're like, okay, so we explored how to interact with the data visualization. But again, to do that, we needed like tools and a bit like technical tools to be able to display, for example, a fair amount of data points in a virtual environment. Also, we needed, we need also to create a library to display a bit more like scatter plots, endpoints, and so forth. So we started exploring multi-dimensional data visualization in virtual reality. So we came up with this this paper, IMAXIS, that was presented at WIS last year, and the idea was like to explore multi-dimensional data. So okay, everything is multi-dimensional. For example, wine is multi-dimensional. It can be characterized with the amount of chlorides it contains, its density, and so forth and so forth. You can find a lot of dimension to characterize wine. And if you want to explore, traditionally, if you want to explore your multivariate and multidimensional wine data set, you will use like state-of-the-art visual analytics visualizations such as scatter matrices or parallel coordinates. But yeah, so we wanted to move away from that and see and design a system that allows you to build those visualization in a virtual environment. So we made IMAXIS, which stands for Immersive Embodied Axes for virtual environments, for visualization of multivariate data in virtual environments. So the concept of IMAXIS is to transport multivariate and multidimensional data visualization into a virtual environment, but by presenting affordances, the dimension of the data set embodied in those axes that the user can manipulate, and by using a very simple gesture-based grammar to build those data visualization in the 3D environment. So just very quickly, yeah, as I just said, we explored this concept of embodied affordances. So the concept of embodiment refers to the taking a representation and put it into a graphical representation, such as air traffic controllers manipulating paper strips to make sense of the data and just like create a 3D layouts, make a layout, and we also reflected on the concept of affordance. How should the system display what the user can do in the virtual environment to grab and assemble those data visualization? So yes, so it translates as this interaction in this virtual environment. So the axes are the embodied affordances of the dimensions of your multi-dimensional data sets. So the user can walk to one dimension, grab it, and assemble it in certain ways to create this data visualization. To achieve that, to have kind of like a modeless system where the visualization system shows you coherent visualization according to the interactions you're performing, we actually designed a very simple spatial grammar that recognizes the layout of the orientation of and the layout of the axis. So basically you have rules that basically the scene is being passed every update frame, and we look at all the axes and we say, okay, if I have two axes next to each other, parallel to each other, you should show me a parallel coordinates. But if it rotates and it becomes perpendicular, the IMAXIS should show the corresponding visualization. So there is this very interesting type of results that happen. So you can grab two axes and temporarily they become parallel coordinates, but if you rotate the axis, you see a scatter plot. So we extended these rules to support more like advanced visualizations, such as scatter plot matrices. So the rule is quite simple. You basically extend your scatter plot by piling up axes on the x and y dimensions. Making a 3D scatter plot or a 3D visualization with IMAXIS, just simply, you just plug another perpendicular axis into the visualization. So I'll just skim through that very briefly. So the idea is like with IMAXIS, we were able to create, to recreate like the basic visualization that are used in visual analytics, such as scatter plot matrices and parallel coordinates. So to build this, well, you grab each parallel coordinate, like, and you plug them next to each other, and then you can obtain this type of parallel coordinate. And yeah, just by exploring. So I didn't do the whole talk, but I'll point you at the paper if you have more details. But we also have this rule of linking visualizations, making visual links between visualization when they are close to each other, so we can recreate this type of 2D connected visualizations. And yeah, so the interesting thing is by exploring this system with like different users and by demoing it and to some data scientists or people that were simply enthusiastic about it, we found like interesting visualizations. And here is an example one of like kind of a circus of parallel coordinates with a kind of a one-to-many connected parallel coordinates 3D layout. And then, yeah, that's another type of interesting layout of 2D scatter plots connected to each other in the 3D virtual environment. And yeah, and actually there are like, since it's kind of supported by this very simple grammar, you can create a lot, there is a lot of things that emerge, such as connecting one axis to a 3D scatter plot, for example, so you can see on one dimension where the data connects into a 2D, a 3D, or a scatter plot matrix, for example. So we also introduced some gamification elements and some metaphors, like, so when you load the system, you have this kind of axis, so this shelf axis, so it's kind of you're kind of in a library, you just open, you enter the virtual environment, and then you see all your data dimensions. Yeah, if you're done with your workspace, you just chuck it away, and you clean the workspace like this by throwing away axes and visualizations. Yeah, and okay, and very maybe briefly, that's a very interesting property of leveraging virtual environments and immersive visualizations. When we made MAxes, we didn't think about creating this type of interaction, but simply by having that rule of always like presenting the visualization accordingly to the direction and the position of the axis, we found this like flexible visualization concepts. And this is pretty interesting. We figured out that by wiggling around parallel coordinates, we were able to, well, resolve occlusion, for example. It just gives you an alternative way to deal with occlusion. I'll just conclude with IMAXes. Yeah, it's a free and open project, so you can download it if you have your own VR setup. It's on the same GitHub. And there is a QR code if you want to get it. So yeah, please download it, try it, send us feedback. It's very fun, and we will also demo it at the coffee break. We have a copy of IMAXes here. So just before we start the introduction to Unity, that's kind of presentation that we just did are kind of the genesis of making reusable tools for. No, sorry, I've got a bit more presentation. I think I'll just skip through that because it's almost 9:40. Yeah, other projects we explored. So Yalong here, a PhD student from Monash, explored geo-visualization in virtual reality. So he's got another paper this year at the Immersive Analytics track where it'll be presented a study on how to present flow data in maps in different setups. It's a very great paper. You should really go. It will be presented on Thursday. Another project, just very briefly, is another project that will be presented this year at InfoVis as well. So another project I collaborated on. It's immersive visualization of aircraft trajectories. And using like, so the focus of this paper is to do how to perform selections in a virtual environment of a large amount of trajectories, aircraft trajectories. So I'll just skim through a little bit. So this is how it looks like. So yeah, the focus of the paper is to leverage bimanual input in virtual environment to select trajectories of interest. And if you don't like aircraft trajectory visualization, there is also an application with DTI brain fiber scans. Okay. Also, another project that will be presented at InfoVis this year by Benjamin here, but mainly driven by Ronald Sikat, is DXR, which is another toolkit. It's a sister project of the Immersive Analytics toolkit. which is much more focused on prototyping, fast prototyping of immersive and embedded data visualizations for the HoloLens, for example, using the Vega Lite grammar. Okay, so just to conclude this introduction to immersive analytics research. So yeah, immersive analytics research is still is a new research thrust, and as Tim just said, there is this book that is available now. So yeah, if you're ready to do immersive analytics research, it's the right moment because everybody starts to build tools, and it's becoming a bit more and more easy to set up these environments. But thanks to the ATK, for example. Okay, so and also something very important, there will be an immersive analytics session this Thursday morning with a few of the papers that I presented here that will be fully presented. And yeah, I guess like this kind of intermediate takeaway message is to say that actually building all the systems is very, very challenging, not only on the design aspect of things, but also on the technical aspect. So that's why we do this tutorial. That's why we build big reusable bricks to build immersive visualization environment. So now we're going to present the IATK, the Immersive Analytics Toolkit, and that will help you. That will basically help you design your data visualization into a game editor, and eventually visualize them in virtual reality. So Andrew will now show you how to manipulate Unity if you have no experience with Unity. And if you have a bit of experience with Unity, I really encourage you to really follow Andrew, who has like several years of development in Unity. You were a game developer for 5 years, and now he's doing his research mainly using this platform.
So the point of this section is just to give everyone a brief overview of Unity. If you haven't used it before, this will get you up to speed on how it works. If you have used Unity, maybe you will learn a few tricks of how to speed up your development. But the point is that the IATK is built on top of Unity, so understanding how to use Unity is essential. So in this section, we're going to cover learning the layout of Unity. We're going to learn the component architecture of Unity, how components speak to each other, and build some simple demonstrations of physics. We're going to create some custom behaviors so you can start to see how you can script game objects. And lastly, we're going to learn the hierarchy that Unity is based on. So this is the Unity editor. Yours might look a little different. I'll just jump into Unity here. So I've got a new clean scene here. Yours might look a little different to what it appears as in the slide. If you're not comfortable with Unity, then you might want to switch the layout, and you can do that from the drop down in the top corner here and set it to 2x3. And then yours will look exactly the same as this overview. So in terms of the Unity editor, there's lots of different components in it, and it can look a little bit overwhelming. But if we step by step go through each of the components, you'll start to see how everything fits together. So Unity itself is based on this concept of scenes. So it's essentially a game object, and the way to think about how you're building these games or applications is that you're essentially a director. You have a scene which has all your objects and actors within that scene. And then you have a game window down here which actually captures the action of the scene. This is, in cinematography terms, this would be what your camera is capturing and what your audience is going to see. So that's our scene window, that's our game window. We have a hierarchy, which we're going to go into depth a bit later. But the hierarchy essentially is the structure of your scene. You can create complex hierarchies, and that allows complex object interactions, or you can have a flat hierarchy, and we'll go over that in a minute. You have an inspector, so what that lets you do is you can inspect properties of objects within the scene, and that'll let you change, how things look, how things react, and so forth. And then finally, you have your project window, and this contains everything in your project. It will contain your data files. So once you start using IATK, you're going to be putting your data files into the project, and then IATK can read it out of that project window. So the first thing about learning Unity is that you want to be able to navigate the scene. And there's 5 tools at the top, and in 2018 there's actually 6 tools. But what they let you do is they let you control the scene, they let you control the objects within the scene. So in this case, you can see here we have the hand tool, the translate tool, the rotate tool, and the scale tool. Each of these tools actually map to the QWERTY keys. So if you want to use the hand tool, you press Q. If you want to use the translate tool, you press W, and so forth. So we're going to start off with the hand tool. So I'll jump into Unity here. And this is our clean scene. When you create a scene in Unity, all you're going to have to begin with is a main camera up the top, which captures your scene, and a directional light. So if I actually disable that main camera, we see that the game window goes, nothing's rendering. So if we re-enable that, this is going to be our main camera capturing the scene. One last thing about scenes is that the way Unity runs is you set up your scenes in the scene window, and then you hit run, and that gets the action happening, and then you can stop the action again. Everything will reset to how it was before you ran. So we can demo that as well. But first off, we're gonna walk through the navigation tools. So I can go up to, we're gonna create an object in the world just so that when we're navigating around, we have a point of reference. So if we go up to game object, we're gonna add a 3D object and we're gonna add a cube. And it's created my cube in the center there. And the first tool that we're gonna use is the hand tool, which is gonna let us pan around the scene. So I can click on that hand tool, or as I said before, I can hit the Q key and I'll jump straight to the hand tool. Now the hand tool, if I use the scroll wheel, it lets me zoom in and out on the center of the scene view. But if I left click and drag, then I can pan around like this. So I can pan left, right, up and down. If I want to get a little bit tricky, I can actually right click and it goes into this first person view. Like, I don't know if anyone here plays first-person shooters, but they let you move around, they let you pan with the mouse. And you can see underneath this little eyeball, you might be able to see the little eyeball, there's actually a little Tetris piece, which actually represents the WASD keys. And what that lets us do is if we press W, we're gonna zoom in. If we press S, we'll zoom out. And if we press A and D, we'll pan left and right. So this is a fairly common way to move around in first-person games, and you can replicate it here by clicking the right mouse button and controlling it like this. And lastly, to move up and down, you can use the Q and E keys. Now, sometimes your object will go out of sight of the scene view. And when that happens, you can hit the F key for focus, and that'll let you focus on the object no matter where you are. The other way you can focus is by double-clicking on the object, and again, that will take you back to focus on the object. So that's quite nice. So that's navigating the scene view. I guess one of the things to think about when you're navigating the scene view is that you're the director, you're like this omnipresent entity in the scene, and the actual camera that's capturing the game down below, you can actually see within the scene view. So I can focus on the camera here. Let's go back to my hand tool. I can actually see that's the camera frustum there that's capturing the 3D world. So that's quite nice. The second set of tools are all about manipulating objects within the scene. So you have the move tool, and that lets me move game objects along axes in the world. So let me just focus on this cube again by pressing F. So this is my cube, and as you can see, once I select the move tool, I get these gizmos appearing that let me manipulate the object by moving it around in space. So what I can do is I can drag the object along the Z-axis, I can move it along the Y-axis, or I can move it along the X-axis by manipulating these widgets. The next tool along is the rotate tool. And again, it lets me rotate along axes of the object as such. And then the last tool that we'll go over is the scale tool, which lets me scale objects. So I can grab each axis and scale along that particular axis, or there is actually, in the center of the object, there is actually this gray cube here, which actually lets me scale the entire object up and down. And those are the basic interaction tools that you'll care about today. There is a couple of other tools here. This is the rect manipulation tool. So if you start doing user interfaces in Unity, you're going to be wanting to use that tool, but we're not going to do any interfaces today. And lastly, there is this what I would call an Uber widget, which lets you translate, scale, and rotate using the same widget. So that's the basics of navigating the scene in Unity. And the next thing that we need to talk about is objects and components. So essentially, Unity is based on this concept of a component architecture. So I think somewhere in the late 90s, object-oriented programming was very popular, and perhaps for a brief period, game engines were based on object-oriented architectures. So if you had if you wanted to create a tank, for example, you would subclass a vehicle object, which would subclass a game object, and that's how you would describe your behaviors of your game objects. But what people quickly figured out is that sometimes you want multiple game objects to share behaviors, but they're actually different classes of objects. And the way you get around that is by using a component architecture. So in a component architecture, what we have is we have a game object. We have game objects within the scene, and we add components to those game objects that describe behaviors that we want to add to those objects. So for example, this is a very simple object which has a mesh, which might be a cube, or it might be a scatter plot, or it might be a person. And then we have the renderer that describes how to render that mesh. And then we have several behaviors that describe what happens when I click on it, or what happens when it hits the floor, and so forth. So the idea of these behaviors is that you can create lots of small behaviors and then you can add them to multiple objects and build up these quite complex behaviors in an encapsulated method. That means that you can reuse code very easily. So in terms of Unity, everything in Unity is a game object, and all game objects have a transform component that describes their position. So when you create a game object, every game object has a default component that is automatically added by Unity called the transform. So if I jump back to Unity, you can see here, this is my cube, and it has a transform component just here, which is automatically added. I can actually create an empty game object, which has, is essentially nothing, but it also has a transform, so it has a position in space. And so when you're doing app development in Unity, you might have a lot of game objects which aren't physically anything in the space, but they'll still have a location. So in terms of components, as I was saying, there's several types of components. We have geometry components that let us add cubes, spheres, so forth. We have rendering components that encapsulate materials. So Unity is based on this concept of materials that describe how something renders itself and components of how that particular thing renders, such as textures and colors. Other types of components are physics components and custom behaviors. And so what we will do now is a short demo of actually adding some built-in components to our Unity scene. So I have my cube here. What I want to do is I want to create a couple of game objects in the scene. So I will create a plane. I'll go to, so there's a couple ways you can create objects in environment, you can go up to Game Object, 3D Object, and then select some of the primitives, or you can right-click directly in here and go 3D Object and select Plane, and that's what I'll do now. So this is my world. If I run this right now, see, it thinks for a while, and I can tell that Unity is running because those buttons are blue. Sometimes you kind of miss when that actually happens. Yes, sorry. So what I like to do in Unity is actually to go down to Edit Preferences, and what I want to do is change the color of the editor skin. Play mode tint. If I play now, you can see it changes the color of the editor. This will become a bit obvious in a second why I like to do this. But if I hit play now, the editor turns blue and I know my scene's running. Right now it's not doing anything. But one of the interesting aspects of Unity is if I edit this scene while it's playing, I can, create some crazy sort of setups, see how it actually behaves when the application's running. If I hit stop, everything resets back to how it was previously. That's a nice feature of Unity because it means you can quickly iterate a lot of different behaviors and experimentations, but then it cleans up the scene afterwards. But what it also means is that if you're in run mode and you go, oh yeah, I really like the position of this particular cube here, this is perfect, and then you hit stop and it resets, it means you lose all that work. So tinting your windows, a really nice cue to basically say, hey, anything I do now is not going to be saved. So that's our scene now. What we're going to do is add a really basic physics behavior to that scene, just so you can get an idea of how simple these various components actually can build complex behaviors. So I'll click Add Component, and I want to add a rigid body. So the rigid body basically tells Unity that this object is now part of the physical world and it's going to react to physics in the world. You can see that the rigid body component exposes some various properties such as mass, drag, angular drag, so the drag that occurs when it rotates. It's got a Boolean to say, is it affected by gravity? Is it kinematic, so is it stationary in the world? And a bunch of other constraints, which we'll talk about further down the track. But just by adding this single component, if I hit run now, what I see is that that cube actually reacts to the physical world. And so you can see how basically by adding simple behaviors, I've started to create a complex scene. And again, the nice thing is in the scene editor, I can play around in the scene editor. I can experiment with different setups. I can even create, as the game is running, I can create new objects and add complex behaviors to those objects. And Unity will will do all the processing for that. Whoop. And there goes my sphere. And again, if I stop, everything resets. I've lost all that work, but maybe I figured out how to move forward with the system. So that is in a nutshell Unity components. Is there anything you want to add to that? So the next step beyond that is custom behavior scripting. So in IATK, you can do a lot of work in IATK without doing any scripting at all. But if you want to start building your own complex interactions or visualizations, you're going to want to jump into scripting a bit. Again, custom behaviors, the idea is that you're creating little components of code that affect game objects. So what I want to do now is I want to add a custom behavior to a game object in the scene and just show you how easy it is to script some simple behavior to a game object. So I'm going to add a cube, another cube. So I'll go up to game object, create 3D cube. And there's my cube there. And I think what I want it to do is I want it to undulate up and down by itself. So the way we can do that is we can go, we can click Add Component here. Now by default, Unity's got a bunch of different components that expose lots of different behaviors, but we're actually going to create our own behavior. So I'm just going to call this my InfoVis behavior. And the thing is, like, you could call that anything. You know, you could call that Jerry. It doesn't really matter what you call it. It's just a reference. So I'll double click that and open it up. It's just thinking a little bit, and here's my source code. So this is a basic behavior in Unity. You see it's already filled out a stub class for me, which is great. All behaviors start off with a start function and an update function. So in the start function, you initialize any values that you want to set up, and then in the update function, the update is called once per frame, and in the update function, you might do some sort of movement or anything that you want to update every frame that's rendered. So what I'm going to do to begin with is I want this object to move up and down, and I want the height that it moves to be controllable by the user. So what I'm going to do is I'm going to create a public variable, public float, and I'm going to call it height, my height. And I'm going to give it a default value of 1. So in Unity, all the units that you see, so all these, this grid here, actually represents 1 meter. If you create a cube, it's 1 meter squared. If I move something up 1 unit, it means it's moved up 1 meter. So by default, I want this object to move up and down 1 meter. And the great thing about Unity is I jump back to my script here, and what it's actually done is it's exposed automatically that public property to the user. So it says my height here, and I can, if I hover over that, I can either type it in directly, so I can go, I want it to move 10 meters, or I can hover over it, and I get this little left and right arrow. So if I click and drag, I can move that value up and down, and the really nice thing is I can keep moving the mouse left, and it will create a massive value for me. So that's nice that it automatically exposes these things for me. If I want to get a little bit trickier, I can actually add an attribute to that property and say, I don't want it just to be a float. I want it to be a float that ranges between 1 and 100. So I'm adding some constraints to anyone that uses this script to basically help protect any errors. So now Unity's reloaded, and you can see that my height, instead of being just a value, is actually a slider that ranges from 1 to 100. So I think that's a really nice feature of Unity. So we've got a height that we want to undulate up and down, and now we want it to actually do that behavior. And we can do that in the update method. So as I said, update's called once per frame. So you know, if we're running 60 frames per second, we're going to get this update called 60 frames per second. So what I'm going to do is I'm going to create a vector 3. So in Unity, all positions, all scales are described in vectors, 3-dimensional vectors. So I'm going to grab my current position by saying transform.position. So what I've just done there is I've referenced the transform component, which is actually this component up here. So Unity actually lets components reference other components on the game object. The other way to do it would be to go get component and then pass in transform. So that's exactly the same. It's just a quick way to get there. So that lets me access the transform component, and it lets me access the position of that transform component. So if I jump back to Unity, I should just quickly say this transform represents where the object is in the game world. If I manipulate things in the scene, you can actually see the transform component updates to reflect that. So I've got my position. What I want it to do is I want that position to move up and down. So I'm going to call, I'm just going to do a sine wave, and I'm going to do time since level load. and then I'm going to say and then I'm going to copy it back into the transform. So anytime I change the position like that, I need to copy it back into the transform. So this 3 lines of code will basically grab the current position. It will let me set the Y component of that position using a sine wave. I'm using this function called time since level load, which is an increment in time. So I'll know at the start it'll be 0, and then it'll increment from there. And then I'm copying that position back into the transform. So if I jump back and run it now, so you can see let me just move this down. My cube is moving up and down how I like. One of the things is, I've done this, and manipulating my height doesn't do anything, because I wanted that to affect the height of the cube. So while this is running, I can jump back into Unity, and I actually want to say pos y equals sine, but I want to multiply it by my height now. Jump back into Unity. You'll notice down the bottom there's this little tiny spinner. That means Unity is recompiling the code. And once it's done, if I adjust that height now, I can actually see that my game object is reflecting that height value. So I can control that very nicely. So I think that's a nice aspect of Unity, which you don't see often in old game engines, is that you can edit the code and it reloads as you're running the application. If you do a lot of JavaScripting, maybe you're used to this sort of behavior, but it's nice to see it in a 3D engine like this. So that is creating custom behaviors. One little tip is that if I'm running and I edit, okay, I'm running and I want Unity to remember this position when I quit, I can actually go up to the cog menu up here of a game object, and I can select copy component. So now when I stop, I go, yep, I'll keep these values. I can actually go paste component values, and then Unity will remember where that object was. Next, we should talk about the game object hierarchy. Unity is based on a scene graph. So the scene graphs describe relationships between objects in the space. In Unity, you have this concept of world coordinates, which is relative to the world origin, and you have local coordinates, which are relative to the object's parent. So to explain a bit further, Unity actually lets you parent game objects off each other. So right now, our scene here is pretty flat. We just have a flat list of objects. But we can add more objects to this and create more of a hierarchy by actually selecting the object. I'm going to use the contextual menu this time, go 3D object, and I'm going to create a capsule. You can't see it at the moment. Well, you can see it, but it's actually co-located with that cube. It's right on top of that cube. So the cube, in its position, its relative position to its parent, which is the world, is at 4 meters. But the capsule is relative to its parent, and it's in the center of the cube. So what we're actually going to do is we're going to move this over here. We can see, you can start to see how you can build up a hierarchy of coordinate systems. So the cube is 4 meters to the left of the world, to the right of the world, and the capsule is 2 meters to the right of the cube. And this is kind of nice because if we're doing this sort of undulation, I can get those 2 game objects to move simultaneously. But maybe what I really want to do is I want the capsule to undulate relative to the cube. So what I'm going to do is I'm going to jump in here and I'm going to add the script that I just added. And right now that does nothing. And that's because if I jump to the code, in this code here we're actually when we say position, you can see the little snippet down below says this represents the position of the transform in world space. So generally, if you're manipulating positions in Unity, you're actually working in world space, which is sometimes a bit backwards for people that think in 3D graphics. So what we actually want it to do is we want it to transform the local position. So that's relative to the parent. So I jump in there, I change position to local position, and I jump back to Unity. You can see that it's reloading because this little spinner down the bottom. And then now I have the cube. The cube is moving up and down, and then the capsule is moving up and down 1 meter relative to the cube position. So hopefully that kind of gives you an idea of how these coordinate systems build up. Last piece before we jump into the actual IATK is I just want to quickly go over how you set up an augmented reality or virtual reality scene. And generally it means you just drop the prefab for whatever system you're using into the scene. So if I jump back to Unity, this already has Oculus set up. So I can jump into Oculus and there are a bunch of prefabs already given. So these are bits of code, bits of objects. These are default objects that Oculus has created for me to make my life easier. And I want to add the OVR camera and the avatar. So this gives me my camera rig. And actually, if I run that now, just with that, it should do the tracking. So you can see, just by adding that camera rig, I get virtual reality tracking from the Oculus. And then if I want to add the controllers into the scene, I grab the local avatar, and I should see the controllers. In theory, I should see the controllers. You'll see the controllers if you do that. So every virtual reality system, every augmented reality system probably has their own SDK. You're going to need to drop those prefabs in. Unity's heading towards standardizing all this. So instead of adding these prefabs, I can actually go into project settings, player. And they call it XR, so XR kind of covers everything in their mind from augmented reality to virtual reality to everything else. And I can hit virtual reality supported. And you can see that, so even without the prefabs, Unity's starting to move towards standardizing all this sort of development. So that is a brief overview of Unity. Hopefully it gave you some tips, but it should give you a good groundwork to actually understand how to use the IATK. And I'll pass over to Maxime to take the next bit.
All right, so we have another 20 to 25 minutes before the coffee break. So now we're going to talk about the Immersive Analytics Toolkit. So how to leverage this type of very nice environment where you can create a 3D space, create like physics behavior, integrate virtual reality or augmented reality, and yeah, how do we bring data visualization and visual analytics in this type of environment? So very briefly, I think everybody wants to have live demos and stuff. So what can we visualize with IATK? So we can visualize quantitative multidimensional data, relational temporal data, flow data, graph data with some custom scriptings, but we're going to bring that very soon into the editor. And we can basically create all those type of visualizations just by manipulating these scripts. So I'm not going to describe them all here. I'm just going to show you how to build them live with you. Just a very kind of a note, reflection note. So so how many people here started exploring data visualization using Unity? 1, 2, 3. Okay. So the default, like what we do usually is we leverage those game objects that Andrew was showing, right? We can just create a cube, we can instantiate it with the code. But the problem is this type of approach doesn't scale. So it's very easy to manipulate. We can add custom scripts and so on. But if you have like a data set that is fairly big or a bit complex, then you're going to hit some like limits of the system. So yeah, for example, on the HoloLens, you wouldn't be able to visualize more than 1,000, a bit more objects from 1,000 to 10,000. But on a high-end VR PC, yeah, you may be able to deal with 10,000 objects. So yeah, that's why we created the Immersive Analytics Toolkit, which is actually a lot of like technical code to let you just instantiate lots of data points, lots of lines, lots of cubes and everything without having to deal with how Unity handles that, and basically create your AR, VR visualization. So it's Windows only. I mean, if you have a Mac, you can just create the visualization and so forth. The problem is the VR market is heavily focused on and AR VR market is heavily focused on Windows. So all the NVIDIA drivers are optimized for virtual reality on Windows machines and so forth. So yeah, I guess for now, if you want to develop VR, you should probably use a Windows environment. So there are still a few issues. You can't use on the Mac. You cannot use the compute shader and the geometry shader at the same time in Unity. So yeah, if you have a Mac, just use Boot Camp and install Unity on Windows. Okay, very briefly, the structure, and then I show you how it works. So it's basically the A8K is a bunch of bricks that we created. So the first brick is I want my data in Unity, so I need a data utility brick. Then there are those core graphic utilities that can be reused by using the code. So basically, these are a set of class and shaders that we made to instantiate like up to 1 million data points and have a very high frame rates in virtual reality. Then yeah, we created this API to control the data brick and the core graphics. So the A8K is a visualization toolkit, and actually it comes with a visualization tool that we built with our toolkit, which are all these visualization utilities that I will show you how to use right now. So okay, so let's start in Unity. So who has Unity running with A8K now? 1 person, 2, 3, 4. Okay, so thanks. I will. Anyway, I'll go very, very slowly. So if someone has a problem, maybe Andrew can help. So I'm just going to show you now how to create the hello world of A8K. So what we're going to do is first we want to clean the Unity editor. So as Andrew showed you just now, Unity is like really designed to as a game editor. It's very nice, but it has a couple of annoying things enabled by default, so which are gizmos. So what you want to do, so if gizmos are enabled, you will see a lot of like meta information and so forth. So what you want to do is you want to grab this selector, put it to 0, and disable 3D icons. Yeah, so if you have if the selection outline is enabled, so you see when you select an object like this, when you have just a 3D simple object like this, it's fine. But when you have a visualization, it's really annoying. So you don't want that. So you click on Gizmos and you disable the selection outline. There is this very nice horizon that is designed for basically when you're in virtual reality. So your perceptual system sees a bit of a horizon. But for data visualization, sometimes it's a bit annoying. So what you can do is simply you can click on that icon here. So you see this kind of landscape icon. You can click it, and it will change your background. Yep. So if you disable like this skybox thing, you get like kind of a neutral background. And just finally, now you have a grid. Okay, let's start exploring the A8K. So there is a tutorial folder for the people who have it. You can just simply create just a new empty scene, and we're going to explore how to import the data in the scene. So if people here came with their own data set and they want to visualize it with the IATK in the Unity editor, you should have a CSV or a TSV. Actually, it supports columns, semicolons. But your spreadsheet should be very clean. So if you have like weird symbols in some cells and everything, we don't really handle that yet. Just make sure open it with Excel and something, make it clean. But otherwise, we have a bunch of sample data sets that are kind of that have just different interesting properties. So we have the Dogen data set. It's pretty interesting because you have categories, continuous dimensions, and temporal dimensions. We shared a bike path data set as well to show how we can create trajectory visualizations, and there is the wine data set as well, the one that was presented in IMAXIS. Okay, so let's jump into it, and let's do the hello world. So the hello world of IATK is to create a CSV data source, so a data source, which is a game object. Because, as Andrew said, in Unity, everything is a game object. So how do we create that? So here we have the hierarchy window. So we can right-click. And here, if you have imported the IATK folder, you'll see a new menu showing that you actually have the IATK facilities. And you can create a CSV data source. And here you have this object that appears here. And if you want to bind a data set, so I can navigate to my dataset folder. A couple of practical things. I can temporarily lock my game object here by using this lock at the top right corner. And I just browse my datasets. What do I want to visualize? Here I've got a bit of a search function here. I can type in Dow Jones. Okay. I get the Dow Jones data set. And here, what I did, I just click, drag, drop, and voila, you've got your data in Unity. You cannot visualize it yet, but you have everything is loaded up in memory. And now you simply have to create a data visualization to visualize your data. So similarly, we right-click the hierarchy, we navigate again to the IATK menu, and here we have a few more stuff under CSV data visualization, but we're just going to focus for now before the break on the visualization class. So we click visualization, and here again we have between brackets those IATK objects. So just before we had the data source, so we have this default name new data source. If you want to call it something else, you just rename it here. And you have the new data visualization. So how that visualization know what to display? Well, it requires now we just have to bind the data set to the visualization, right? So again, we can click and hold this data source, and we drag and drop it on the data source. And here, what you should see happening is that the GUI changed because it's understanding that we just attached a data source. And by default, here we have this visualization type menu. I'm going to make it a bit bigger, where the default visualization to explore your data is the scatter plots. But a bit after the coffee break, I'll show you how to make more advanced visualizations. Okay, so our scene is empty, and now we're going to start building our scatter plot. So here we have a group called x-axis and a drop-down menu. So if I click my drop-down menu, I see all my dimension of your CSV or TSV data. So we're going to start to explore this visualization by binding the date dimension. So you should be able to navigate now by yourself because you heard you were carefully listening to what Andrew was saying. So yeah, so if sometimes when you create an object, it appears somewhere else in the world, so you need to navigate back to where it is. So okay, so here I've got my date axis. So we're simply going to start by creating a 2D scatter plot. And then we, on the y-axis, we're going to put the volume of transaction. So yeah, we're talking about the Dow Jones data set here. So here, we cannot see it yet, but I've specified a 2D scatter plot. Now we're going to navigate our kind of data and visual variable bindings, sort of like grammar of graphic editor. And we can choose the geometry. So let's start simple. Let's just choose points. And here, with like just a few sequences, we have like a 2D scatter plot in our immersive environment. Okay, next step, let's design our visualization. You can bind a color dimension to the data points. So if we click again, so similarly to the axis drop-down menu, we can bind a continuous variable to a gradient of color, for example. So say I want to see the lowest dimension. Well, what I want to do is to edit the color value. So here you see there is a dimension color menu, and there is this kind of white, kind of totally white but default color. And if you click it, you see this mini gradient editor appearing. So this is the gradient editor of Unity, and now I want to say that my low values. I have a bunch of presets, gradient presets here. Yours are probably empty if you just installed Unity, but we'll create a new one. So I want to say that my lowest values are, like, let's say, use a cold color. So let's take a blue color. So if I click, I kind of like, and you see that the A8K reacts to the change of color in real time. So I wanna say, okay, the lowest color, the lowest values will be blue, the highest values will be red. And what I can do is I can actually directly manipulate my gradient and say, okay, at 50% of the value, I can basically move my gradient key. And yeah, if you want to be crazy, you can like edit your gradient and add more colors everywhere, but I don't really recommend to do that because it becomes a bit hard to visualize your data. Okay, so now we created a gradient, and if we navigate to the top left of our visualization, we have a key appearing here, and it's telling us that the color is into the low values dimension. Okay, so let's keep going with the design of our first immersive visualization. Now I'm going to navigate down to the size dimension, and I'm going to explore. I want to say, okay, I want to bind the size to the percent change price. So if I zoom in here, so I see that the data points of my scatter plots have changed, so actually the size now is attached to this dimension, and if, again, I navigate back to my key, I see that everything is persistent. I can understand what the size represents. I can change the size values by moving this size slider, and I can also change the minimum and the maximum size values. Okay, so just before I show you how to create alternative visualization, I'm going to show you what else you can do with this, just with these 2D scatter plots. You can click again on geometry, and so do not click line for now, but we can change to quads, cubes, bars, and spheres, for example. So yeah, we kind of implemented so spheres will be more useful when you have a 3D scatter plot. Speaking of which, let's make our scatter plot 3D because we're in an immersive environment, right? So why not? Let's make a 3D scatter plot. So now we navigate back to our z-axis, and let's attach another dimension. For example, the stock, the name of the stock. So we kind of get directly, we can edit this 3D scatter plot like this. Okay, as I was just saying with this, the interesting thing in this data set, it has like connected components. So it has all the stock values in time. So what I can, what usually like visual analysts do of this type of data, they visualize spark lines. So what I can do is I can click the linking dimension, and I want to tell the AHK now show me the visualization linked by the stock. So nothing happened yet because I'm still using a sphere geometry. But now if I choose a line and I change the size values, I obtain this type of 3D sparkline visualization. But if you don't want it 3D, you can go back to 2D, and it animates back to the 2D visualization. And you can also visualize this as lines and dots. So if you want to see the values attached to each date, for example. So here you see that we changed the visual attributes and the visual styles and so on, but everything is persistent, right? So before we linked the size dimension, and we now changed to a connected lines and dots visualization, and the size is still mapped to a visualization. So maybe I want to put that back to undefined, and there you go. I have obtained my visualization. Of course, it's a dynamic script. I can change the axis values, and what you can see is that it animates. So it's the same in virtual reality. If you change each value dimension, it will change, and it makes this smooth transitions between the visualization configurations. So just by using this script, for example, you can visually inspect your data. So I've got a few more minutes left before the break. What are we going to do with this now is we're simply going to hit play. I'm immersed in my 3D visualization. So I can walk around, I can inspect the values, I can read the dates. Sorry, Andrew. It's great. Like I can walk around. It's quite big. I can change the scale. Yeah. So Andrew is changing the dimensions. Can you do that again, maybe? Mm-hmm. So that you see that even in the immersive environment, I see the changes. So for now, it looks like a bit like Wizard of Oz, but after the break, I'll show you how to bring these interactive components into the virtual environment and keep designing your data visualization into the virtual environment. Okay, so let's take a break for a few minutes, and then we'll explore much more things that you can do with that toolkit. Okay, see you at, I think, 11? Okay, thank you. We were just designing immersive visualizations, like doing the hello world of the immersive analytics toolkit. So before we go back to hands-on stuff, I wanna explain a bit like what is the framework of immersive analytics or designing immersive visualization with IHK. So as I said in the introduction, so IHK is a set of scripts and tools that you can use like on a non-programmatic ways. You don't have to write code to create these immersive visualizations as we saw before, but you can also manipulate and write code with the API, which will be what we'll be showing at the end of this tutorial. But pretty much what's happening is, and I'm demoing it live here, when I design my immersive visualization, I'm sitting down and I've got my Unity editor on my laptop, and I simply hit play, and I'm in my immersive virtual reality environment. So yeah, just really wanted to make that point that the IATK really kind of integrates in your, almost like in your designer mode and your exploration mode, and it can be used as just an extension of your traditional information visualization journey when you explore your data, or you want to create a visual that communicates insights into your data. And speaking of which, let's go back to the editor. So, okay, back to our editor, and I'm going to recreate what I did before. So I'll just do a bit of a repeat, but maybe this time with a different data set. I'm going to create a CSV data source again. So again, I navigate to my dataset folder, and I want to visualize the wine dataset. And now I'm going to create, again, my new visualization, attach my CSV data to my visualization. So that's where we were at before the break, right? We built a visualization, and then we hit play, and we were in a virtual reality environment. So now let's see how we can use like Unity, the Unity editor, as a visualization platform. So let's make a data visualization of a sketch plot of our wine data set. So I've attached the the citric acid on the x-axis and the density on the y-axis, and I'm going to keep designing my visualization. I'm going to get point geometry, and I'm just going to demonstrate how this tool can be used as an actual visualization tool. So when you start Unity, as Andrew was showing, you have like a few gizmos that allow you to manipulate the camera. So what you can do is you can actually tell Unity to show you an orthographic mode. So now you don't have any more perspective distortion in the editor. And so you have like a purely 2D orthogonal plane. So that's a step towards more like 2D. I mean, with that type of setup, you can do like proper 2D InfoVis. But also, what can we do? So here we have like a nice wine data set, but we see that we have a few like outliers. And so if we look at these handles here on the x-axis group and the y-axis group, we have those range sliders. So let me eliminate the outliers, so I can simply renormalize this, and just by using like direct interaction, direct manipulation, like, okay, this is probably what my data looks like, right? So, okay. Let's attach, okay, another demonstration another thing that I didn't show before. Let's use the color dimension to show, for example, the type of wine. And so before, I showed you how to attach a continuous variable, bind the continuous variable to the color of the data points. What you can do now is, if you have like a discrete variable, like such as white wine and red wine, you can click on it and explore the color that you want to use for the white wine. So white wine is what? Not really white, right? It's a bit yellow. So let's explore yellow. Let's look at the hue here. Nice. Okay, get something nice. Red wine. Red would be a bit too red, so let's go a bit more purple. Nice. I've created categorical coloring of my data. And as I was showing before, now we have this key that you see also in virtual reality, and that tells you that's what's the color key, right? So you've got like that color for white and that color for red. I can still freely move my camera, but what I can do, every time I want to go back to a orthogonal visualization, I can leverage these widgets. So if I click on this x-axis, I get this type of 3D rigid body rotation. And the nice thing with this is, for example, if we want to do a 3D scatter plot visualization, let's attach the chlorides. And I don't see it here, right, because I'm using a orthographic projection. But what I can do is I can navigate my 3D scatter plot just by using the components, the default components of Unity, and I get this sort of like scatter dice-like navigation, just like this kind of 3D rigid body rotation, which is kind of a given interaction tool in Unity, but that we can leverage to support our exploration. Oh, by the way, we could filter more outliers here, so let's do it. Oh, we see a nice cluster separation. I wonder what it looks like in 3D. Well, I can simply press play. And again, it's a bit further down. Scene. I get my visualization. Oh yeah, I promised you how to show you how to do that in virtual reality, and I'm going to show you that right after that. Okay. So now I'm on. Can you hear me still? Yeah, I guess. So yeah, now I was just a moment ago, I was visualizing my 3D scatter plots and my 2D scatter plots on my desktop. And I just put my headset on, and I click play, and now I'm immersed in my scatter plot, and it's pretty amazing. But the only navigation interaction that I get is just moving around, right? So what I want to do now is I want to interact a bit more with my data. I want to be able maybe to grab it, rotate it, because as we know, there's been a lot of research showing that when you leverage like 3D rigid body rotation in 3D scatter plot, you may see structure. You understand a bit better the structure of your data with occlusion and so forth and so forth. So, so really, like we're just the one here with the VR headset, but just for your information, you can use this tool that is called VRTK for the Virtual Reality Toolkit. It's a project that basically integrates all the technology, the different virtual reality technology, and makes a high level and an abstracted layer of what virtual reality components you can get into Unity. So say if you have a HTC Vive or a Cave 2 or a Meta headset, and you have input and output, this guy who made this tool here made an abstraction, and basically you can use like high-level components that map like the hand position, the buttons, the camera, and so forth and so forth. But also, he kind of like redeveloped all the interactions, the default virtual reality interactions that you can leverage in a virtual environment to explore your data. And what we're going to do a mini activity now. Well, I'll probably it will be just me showing it how to do it, but that's kind of acts like as a good tutorial. I think if you want to go beyond simply clicking hit and play and seeing it simply in 3D. So now we're gonna see how very simply in a few steps we can make our immersive visualization interactive. I mean, how can we grab it and rotate it and place it in space? So here I'm back in my Unity editor, and so if you get the GitHub of the VRTK and you put it here, you will have like this VRTK folder. So yeah, so here you have the ATK, VRTK. So when you have that, you go to Window and VRTK, and then you can invoke that menu that sets up interactable objects. So I won't go too much into details. There's like loads of tutorials on the GitHub of VRTK, but very quickly I can select my new visualization here, and I want to say, okay, highlight maybe green when you get collided by a controller, and I just press setup selected object. Okay. So here, as Andrew was saying just before, our 3D objects in Unity have like components, physical components. So when you add a behavior, a VRTK behavior, you get, by default, you get this rigid body. So we probably want to disable use gravity. We're going to disable gravity, because if we hit play, then the object's going to fall infinitely onto the ground. So we probably don't want that if we don't have like a ground. So we want to set up this kinematic property. And also, we need to define what's called a collider in the Unity environment. So again, we have to keep in mind that we are in a video game editor here. So you have to be a bit a visualization designer, but you have to be also a bit of a video game designer. Just think in terms of like how do objects interact with each other in a video game. So most of the physics of video games is based on collisions. And so if I want to use my controller and grab an object, well, I probably need to tell Unity that it should listen to collisions between these two objects. So what I do is add a box collider component to my visualization here. And I have this square here, which is actually a cube, if I rotate around. But now I'm going to edit it to say, OK, so I click this Edit Collider button, and then I will edit it. I'm just specifying where the hit collision is going to happen. So now I've designed just that face. Now we'll take that here. Maybe one more turn. Yeah. So this green outline here is just a visual guide in the editor. So if I select my object in the hierarchy, it's not interactable anymore. So now, and I won't be fooled another time, I will move it a bit further up before I hit play. I'm going to hit play. I'm going to put my head-mounted display on. And OK, so I'm back in my virtual environment here. I've got my controllers. Oops. Triggered. Okay, so now my controller can collide with my visualization, and I can push a button on my controller and grab my visualization, and I can say, okay, I can inspect it like in a very different way. It's a bit less rigid than just like flipping it around in the editor, and say, okay, I find that interesting. I put that here. Okay, so I can, if I have many of them, I can collide with them, like organize my workspace. Cool. So something a bit like the default behavior of this, when you say, can you see my controls properly actually on the feedback? That's another design thing. I don't know what you're seeing. That's an interesting research question for me. So what's the default behavior of this grabbing behavior is it goes back to the origin. So let's say I want to grab at the center of my cube. It like automatically translates to the origin. So what I want to do is go back to my editor and simply scroll down to the interactable object script. And here I've got a subscript of VRTK that is called VRTK child of the controller grab attach. It's just like, if you go on the VRTK webpage, you will see heaps of ways to grab objects and slide them along and everything. So here I can enable what's called precision grab. And I hit play again. And this time, the controller remains like the grab mechanism, the point where I grab the visualization at is attached to the position and the rotation of my controller. And this is really, really powerful because what I can do is I can define a pivot point, right? So I want to grab the 3D visualization at the junction of the two clusters in the 3D environment, right? So I can grab the middle here and just inspect it here. But now if I want to grab that data point and rotate around that data point, I can get that almost for free. Just a few clicks in the Unity editor. So this demo shows you like how to really just leverage the I80K, create a visualization, and take the VRTK, so another component that everything lives together really well, and kind of very simply, you can design this kind of advanced interaction technique with like tracked objects and things like this. Okay, so before I move on to other type of visualization, I want to show you maybe a bit more things that you can do with the visualization component. And this is kind of an interesting visualization to play with. So what I can do is I go back to my visualization script component, and here there are like a couple of menus that I haven't mentioned yet. So what we did with IATK is we exposed like a bit like the parameters, the graphics card parameter. So something that is usually done in visual analytics, there are a few systems that use that, is you can change the blending mode of your data object. So when you draw a lot of points at the same place, you can change the blending mode in the graphics card, right? And so you can automatically, for free, see where the clusters appear in your data. And so that's in IATK. You simply navigate to blending mode source, and you choose 1, for example. Not for example, you choose 1, and 1 and 1, okay? So here what happened is I get a view of where there is a lot of overdraw, and that overdraw indicates where clusters are in my data. Okay, so let's move on to another type of visualization. So for now, I just showed like 2D and 3D scatter plots. Let's create a few more things. Now we're going to attach again the data source, and we're going to select the visualization type drop-down menu, and we're going to choose the sketchplot matrix. So when you do that, by default, you get that sketchplot matrix. So there are actually many more dimensions in the data set, but by default, we restricted by the default sketchplot matrix is just showing 5 by 5, but you can add dimensions, or you can programmatically do it. And I'm going to show you how to do that in a second. The reason that we did that is even though like what I was just demoing before is like something around like 20,000 data points. If you show a sketchplot matrix of 100 times 10,000 data points, then you're going to start reaching the limit of the graphics card. So by default, we just show a 5 by 5 sketchplot matrix. So again, we see that the only thing that changed in our visualization script is the axis menus, right? So before we used to have just those 3 groups, x-axis, y-axis, z-axis, and now we have a block of x and y axes, but the rest of our visualization script remains unchanged. So let's visualize it as spheres. And let's do a bit of design. Let's attach the, let's go back to our color binding of type and white. Oh, didn't show something, so I'm going to recreate a white wine. So here I can hit that little square here, and it will remember a preset. So next time I go back to my editor, I will have my preset color. So white is that color, and red is that color. It's a bit too red. It's a bit too red, isn't it? Purple red. Okay, it's better. Okay. And here, by default, when you manipulate the sketchplot matrix, you just obtain this 5 by 5 sketchplot matrix. So what can we do though? Is we can leverage the 3D immersive virtual environment. So from that 2D scatterplot matrix, I've got an empty menu of Z dimensions. But maybe what I want to do is extend it. So here I added on the Z dimension, I started to add the type of wine. It's not very interesting. Let's put something else, density. And so yeah, again, I can keep iterating and creating my massive 3D scatterplot visualization. And I can go on and create and start to create like fairly big 3D scatterplot arrays like this. But again, this seems like in 3D a bit of a hard object to manipulate, but by leveraging the Unity editor navigation, we can simply navigate our scatterplot matrix. Again, the filters work the same way, so I can filter the amount of volatile acidity, I can filter the residual sugar. It's listening to all this. Oh, something that I forgot to show in the previous visualization is I can add like a visualization filter, an attribute filter. So here, I think I'll show you that with the scatterplot back when we go back to the scatterplot. Okay, so this demo was how to create a scatterplot matrix and how you can extend it in 3D. And the same, like if you want to see it in VR, you just hit play and you'll see it in virtual reality. So moving on, and let's explore the other available, default available visualization is, for example, parallel coordinates. So if you click parallel coordinates, the AATK will show like a default parallel coordinates. And similarly, the only thing that changed in the visualization script is the group of axes. So we have all those axes that again can be filtered. Whoops. So I can filter by manipulating these. Whoops. So the geometry are lines for parallel coordinates. Similarly, I can iterate through the design, and it behaves the same way as the previous visualizations. Okay. Cool. So I guess before we go to the API manipulation, I'm just gonna show you two more things that you can do with the IATK. For those of you who were in the first part of the tutorial, I showed the iMaxis project, and I'm just going to show you here how we could, if you want to create your own iMaxis with IATK, what we did is we exposed what we call the visual linking mechanism between two visualizations. So here we just like just for the demo, we create two visualizations. Let's design this scatterplot and this scatterplot here. Okay, and so yeah, what we made available in the IATK is this links between visualizations. So what I can do to create this linked visualization is to use this linked visualization sub-item in our IATK menu. So here, so far we learned how to create a data source and a visualization, and now we got a linked visualization. So the linking paradigm is very simple. Well, to link to visualization, you need one visualization source and one visualization target. So as you may have noticed by now, everything is drag and drop based. So when you expose in Unity, so when you expose like a component in the editor, it's expecting an object that contains that component. So very, very rapidly, when you start to manipulate Unity, you can simply drag and drop the corresponding game objects that have the components that some scripts are expecting. So now I specified my linked visualization, but nothing appears, simply because I need to tell IATK to show me the links between these two visualizations. The linked visualization script is actually listening to the position of the visualization, but it's also listening to the design. So if I want to attach like a certain like color to my to one of my scatter plots, well, I can do it, and then we see that the line are colored accordingly. Also, if I want to go from one scatter plot to another scatter to a 2D, from a 2D to a 3D scatter plot, well, I can simply just change it, and the IATK updates automatically the links between the data points. So this type of like 2D, 3D linked visualization are really made easy to define in Unity. Or you can also do simply one axis connecting, just one data dimension connecting to a 3D scatter plot, for example. You can explore the full combinations. So we can make that code dynamic at runtime. So we made this little activity for the people who have their Unity running with the IATK, but I think I'll demo it live. Simply, I'm just going to show you how very simply you can like write a very simple mono behavior script that Andrew was demonstrating just before, and control the links, the appearance of the links between the two visualizations when they are from a distance threshold. Here I created this script that I called the distance linker. And let's reflect back a little bit to what Andrew was showing you before. So in Unity, Andrew demonstrated that you can just grab an object, its transform, and so forth, and change its behavior. And you change the behavior of an object by grabbing the component of that object and setting values. So what we can do is create this type of script that here we call the distance linker, and we expose a linking visualization. So my script will be expecting an IATK linking visualization object, and it's going to expect a minimum distance to show the links between the two visualizations. And so in the update loop, so the update loop is like every frame Unity is re-rendering the scene. Well, we can see what's happening, and we can do like runtime behavior. So here, what I basically told Unity to do is, if my linking visualization is not null, I simply toggle the Boolean values which is exposed, which is show links. Okay, so how does it work? Well, simply I drag and dropped the distance linker. Just going to leave it maybe 0 at 70 centimeters. That should activate at 70 centimeters. So the configuration of my initial linked visualization has like the two references of my two visualization, and the show links is disabled. So if I hit play, in VRTK, I can teleport. So if I want to get closer to my visualization, I just point and then I'm closer. So okay, so now I grab my visualization with the mechanism I showed you before, and if I get close to a certain range, when my two visualizations are in range, we can see the visual links appear between the two visualizations. And similarly to IMAXes, you can like explore this dynamic linking system. Okay, so before we go to the last part of before we explore the last part of the tutorial, I'm going to show you another facility in IATK, which is brushing and linking. So brushing and linking, I assume everybody here knows what brushing and linking is. But basically, we designed a brushing and linking mechanism where the brush controller expects a visualization and reads input of the controllers, or actually of whatever object is in the scene. And so we can brush the data points, and then we can link other visualizations, and those visualizations will highlight the selected points. So I'll just demonstrate, just show you the scene. Okay, so here I have my brushed scene. Let's make that a bit more complex. So here I have like 3 visualizations. I should probably color them or change the color. I'm just going to change the color of the ground because it's white on white. Let me create a new material. Ground. Change the color. Make it maybe a bit more dark. And I create material. So that's how you change you can change quickly the rendering settings of big quads or planes, for example. Okay, so here, what does my scene looks like? So I've got my VRTK managers that handles all my interactions in virtual reality and my camera. And I have like my CSV data source, which contains the wine quality data set. And I've got 1, 2, 3 visualizations. And here I've got a brushing and linking, an IATK brushing and linking. So how do I create one? It's accessible just here, IATK brushing and linking. So when you click that, you have a new brushing and linking object that appears. And so what it's expecting a brushing visualization. So again, you just drag and drop the controller, where the interaction is happening. And then you can just drag and drop like the brushed visualization, so where the data points will be highlighted. You can tell the brushing and linking script to show the brush or not, and then you can change the color of the highlight color. And finally, you can specify the brush input. So by default, we implemented 2 brush type. So a sphere brush, which kind of in a 2D visualizations is just simply the intersection of the sphere and the plane. So you can do like a circle, a disk brush, and if you have a very, very small radius, then you can just highlight 1 point. And we also implemented a box brush. And so what the brushing and linking component needs to run is transforms. So again, back to what Andrew was talking about before, every game object in the scene has a transform. So what this script is going to do, it's going to read a position, a local position, and of an object in the scene, and going to see if there is a data point in that scene. And then under the hood, it just propagates the information and then just gives the information to the other visualizations. So let's see how it looks. So my brushing visualization is this one here. So now I'm in virtual reality. Not yet, but cool. Okay, so I can teleport because I'm a bit far from everything. So here, I'm just like, okay. So here I can brush the data points, and I can see the highlighted data points in the corresponding visualizations. So an interesting thing that happens with this sphere that I was talking about is like, for example, as we are brushing with a sphere, when you get closer, you can naturally increase the sphere of the brush. But if you're a bit further, you can have a bit more fine-grained brush, right? So if I want to brush just that data point, I can simply adjust the distance and just brush it. And if I get closer, I get a bigger brush. But all those parameters can be can be set up. And like again, as I showed you before with the linking visualization, you can write a custom script, and you can, for example, modify the behavior of your brushing mechanism. I think maybe just before I finish, let's extend our 2D scatterplot to 3D scatterplot, which is a bit more complex. Okay, and yeah, similarly, now I can brush my 3D scatterplot, and yeah, I can see like by emergence that I'm brushing that sphere. And all that, what I just did is real time, I just changed my visualization configuration, but my brush adapted to the new visualization. Okay, so I have another 10 minutes, and I can show a bit more activities and custom behaviors that you can do with the AI8K. So let me navigate back to my tutorial, get back to my entity scene. Okay, so I'm going to create a new CSV data source again. That's going to actually, I'm going to be able to demonstrate how to create trajectories visualizations, for example. And I'm going to take this data set, whoops, drag and drop this data. And I'm going to create a new visualization, drag and drop. Okay, so here I've got like a data set, just a subset of flights, of interesting patterns of flight patterns. So I want to visualize this as a scatterplot form. So on my, sorry, I forgot to translate this one. So on my x-axis, I want x. It's actually latitude and longitude. It's the latitude and longitude data. And now I want to specify my linking field to tell the AI8K to show me trajectories. So this is like I want to link my data point by flights, and I want to show them as lines. And so here, when I do this, I obtain this 2D visualization, and here I can map the altitude, and I can like view my set of data like this. Something that I would like to demonstrate is this attribute filters here. So we know that we have a limited amount of channels to explore our data by doing data binding with the visualization. But what is quite usual to do in visual analytics and or visualization activity is to do queries. And so here we have a query mechanism, which we call attribute filter. And I can specify, for example, that I would like to filter my data set by which means time. So I just type this, and by default, all my filters are zeroed, but I can just simply recreate the initial values. So here, what I can tell the AI8K is tell me, just show me in my current visualization that range in time of my trajectories, right? So actually, if I move one end or the other of time, I can see the patterns, the temporal patterns, the temporal behavior of my data set. Okay, so as the very last activity, I think, with this, I'm going to show you how to automate this and how to view the evolution of my attribute filter in time in virtual reality. So what I can do here is attach like a custom-made component that I'll just explain to you, that I called attribute animation. Okay. So here I added, so in the I80K repository, there is this custom script called attribute animation, and it's expecting a visualization component. So let's take our own component and put it here. And here it's expecting like a time scale, which basically is what's the speed of time for the animation. So we can go like 10% of the update rate. And we can simply like play the visualization from beginning to end. Also, it's expecting just like a key, like just an action on the keyboard to trigger, but this is just a demo data set, so you could simply change that value in that script here that I'm going to open, attribute animation. Here I've got a key code object. It's just like the key code of the keyboard, but if you have your own like SDK of your virtual environment, just put like button 1 or button A, and then you can trigger the script. Okay, so if I hit play, just going to make sure it's doing the right thing. Okay, just going to reset the color and size. Whoops. Okay, so I've got my trajectories, and if I just put my game window here, and if I hit play, I should see my visualization animating with the attributes that I specified in the filters. So the nice thing again is if I want to see this evolution in virtual reality, how my flight patterns, these stack patterns were enabled, basically I can actually, I'm going to finish this tutorial a bit more comfortable because you can do VR also sitting down. It's pretty good. So yeah, I'm immersed in my trajectories data, and I can observe. Oh, I should maximize the window because you're not seeing much here. Let's do it again. I can simply trigger the attribute animation, and I can see how different planes integrated these stacks to land. Okay. So basically, we've showed all the I80K components, how to create one visualization. Just going to go to that slide that kind of summarizes everything. Okay, so now I just demonstrate how to use those visualization utilities here, which are here in the architecture. So those tools that I showed you how to use were built with the core API and the core utilities of the Immersive Analytics Toolkit. So just to recap a little bit, we explored how to design a visualization interactively, how to do brushing and linking, and how to enable, for example, visual links between the visualizations. But now, what what Andrew is going to present is how we can like write simple code if you want to do like more custom data visualizations, more custom behaviors, and so on. How you can like just simply manipulate the views and the view builders and the shaders and everything. How you can use all those bricks and make it your own. If you think that you cannot achieve exactly what you want with those visualization utilities and you want a bit more freedom, Andrew is going to show you a couple of very nice and very compelling kind of sort of big data visualization scripted. Okay.
Okay, so in this section, we're going to kind of jump into the underlying code of I80K. So everything, as Maxime said, everything that he's shown you so far has been using the Unity editor, and you're just doing a lot of visual editing to build up these quite complex visualizations. And I think throughout that whole period, you only wrote about 3 lines of code or something like that. But actually, the underlying the I80K is a complete API, which you can use to leverage and build your own more complex visualizations. So in this section, we're going to be learning the underlying architecture of IETK. We're going to see how you can programmatically build a scatter plot using a very nice and simple API. We're going to look at just one way we could facet the data and build multiple views, and then we're going to use that faceted data to do a novel accordion interaction. A bit about the architecture. As I was saying, Maxime has demonstrated everything using the visualization class, and that presents a nice high-level abstraction, and you can achieve a lot just with that class. But underlying that, the visualization actually contains what we call multiple views, and which are views on your data, and they're built using a factory class called the View Builder. So we use the View Builder to build views, and they're exposed in the Unity editor. So diving in a little bit, the two classes, View Builder CS and View, use a Fluent Interface Design pattern. So that's kind of D3-like. So if you're used to programming JavaScript, you've probably seen this a lot. The idea is that we chain actions together on a particular object. So we might say object, do something, dot, do something else, dot, do something else. And it's a nice way to iteratively design something visual, like a visualization. So we might say we want to visualize this on the x-axis and run it and then see how that looks, and then go, actually now we want to change the size of something else, and we just chain a function along like that. So this really uses what's called a Fluent Design pattern, and you'll see that demonstrated in a minute. The other aspect that really facilitates visualization in IETK is a framework called LINQ, and that's part of C#. And what LINQ lets you do is, again, it uses a Fluent-like interface design pattern, and it lets you transform input data, such as your data dimensions. It lets you map colors, map data to categories, but most importantly, it lets you do filters and manipulations on big pieces of data. So first of all, I'm going to jump back into Unity. And the first thing that we're going to do once it loads, because I think it's still loading, is see how we can programmatically load a data set. So to programmatically load a data set, what we're going to use is a class in the IETK called CSV data source. Now this data source is actually built on top of a more abstract data source type. At the moment, as Maxime said, we only support comma separated or tab separated data, or space separated data, whatever you have. But it is abstracted out. So if you want to build new types of data loaders, you can. You can build it on top of our framework and load it in and view it in the editor. So we're going to use a CSV data source, which is part of our IETK. We're going to use a text asset, which is a facility that Unity gives us. And then we've created a little helper function here, which will actually load the data source. In terms of how you load the data source, it's actually one line of code when you have all that. It's data source.load. We pass in the data as a string, and then we pass in an optional metadata, which actually, so by default, IETK tries to automatically infer what types of data is in your data file. So whether it's categorical or continuous data. If you want to add any specification to that, you can pass in a meta file, which helps define what your data types are. What I'm going to do is I'm going to create disable this. I'm going to create an empty game object and add a new class, which I'll call my viz. So that just gives me a piece of code that I can start working with. And as I said, I'm going to create a text asset. Text asset is part of Unity, and I'm going to add a data file. Then I'm going to create a comma separated value. And I'm going to call that my data source. I'm just going to put in so everything in the ITK is in the IETK namespace. So ideally you import that namespace using IETK, and then you'll get access to all the code without having to qualify it. So now I put my data source. I'm just going to paste in this function here, which is the create CSV data source. It takes in a string of type data. What you can see is that it actually grabs this game object references the game object that this behavior is attached to. So if I call GameObject.addComponent, I'm actually going to programmatically add a component to that game object. In this case, the CSV data source. And then I'm going to call dataSource.load, pass in the data, and then return that data source. So from that, I can go data source that and create CSV data source. I want to take the contents of my data file and grab the text out of that data file. So these few lines of code will load the data file out into IETK. So if I jump back here, you can see Unity's thinking about what it's doing. And of course, I want to make this public because I want the user to be able to edit this value. Okay, great. So now it's exposed that data file. One thing we haven't showed you in Unity is there's this tiny little bullseye here. If I click that, it actually brings up an asset inspector, so I can actually search for my assets. The asset that we're going to deal with today is Uber drivers. So this data set contains latitude and longitude of particular Uber drivers. If I jump back here, maybe just as a sanity check, I just want to loop through all my dimensions in the data source and double check that it's actually loaded something. Okay, so this little snippet of code here is going to loop over all the dimensions of my data source, and I'm just going to print out the name of the dimension and just make sure that my loading has done something that I'm expecting. Okay, so that's not showing me what I'm expecting. Yep, let's just double check that. Uber. Sorry, that was the wrong data set. Okay, so now if I run it, I should see the names of those dimensions. And I can see this is a data set. It contains date, time, latitude, longitude, and the base of the Uber car. And just to show you, this data set is actually quite a large data set, so I can actually go into my data source and print out the, I think it's the data count, just to see how many data points are in that data set. So that contains 98,000 individual data points. So that's basically how you programmatically load data into IETK. And then the next class we're going to talk about is the view builder. So the view builder lets you build views. To use it, we create a view builder, we pass it in the type of topology we want to create, so it might be points or lines, we're going to use points, and we pass in the name of the view we want to create. Then we call initialize data view with the number of points, and then we set some data dimensions. And as I said, this is a fluent design pattern, so we can gradually build up our visualization by calling more functions on that object. So this is what we're going to do. I'm going to just grab it from my code that I already have. Here. And drop it into Unity. So I jump back into my Unity editor. I want to add this function, just called Uber. It takes in a data source. We'll ignore this gradient code for now and just focus on the view builder. So as I said, the view builder takes in a topology, which we're going to use points. We can give it a name such as Uber pickup points visualization. We're going to initialize the data view with the data count, the number of data points that we want to visualize. And then we call some functions to set the dimensions that we want to visualize. So in this case, I'm going to visualize the lat and long on the x and y dimensions of the visualization. And then just from that, I'm going to comment these out and just run this. So that's all good. That will initialize my view builder. The last thing we need to pass in is a material. ITK util has a function called getMaterial from topology, and we tell it there's a bunch of default setups that we have, including the points, which is what you see when you create a normal point visualization. Yep. So getMaterial from topology we can call abstract visualization, geometry type. There's a whole bunch of different types here. Bars you've seen, cubes, lines and dots, points, and so forth. So we'll be using points for that. And finally, we call view builder, VB, .updateView.apply, and we apply it to the game object of the component that this is attached to. So if I call Uber now from start, I want to pass it in my data source and then give that a run. So I jump into my scene, and what you can see here is that I'll just switch off orthographic. So if you want to switch back and forth from orthographic, you click that little tiny cube widget there, and it'll switch between the two rendering styles. So you can see here, just with those few lines of code, I've actually created programmatically my, my scatter plot. So this is programmatically created. One of the things you'll notice is that it doesn't include the axis objects because they're part of the more high-level visualization component. So this means that if you want to create your own axis styles, or you want to embed these in something other than what we provide by default, you can go ahead and do that. So that's pretty great. Just to demonstrate the kind of the fluent nature of this interface, I can then go, I want to turn this into a space-time cube, for example. So I will go set data dimension. I want to call it CSVDS, so that's my data source. And I want to add a third dimension of date, I think it is. Just double check. Date. I want to pass in the data, and then I call viewbuilder.viewDimension.z. And if I jump back into Unity now, we can see that it's actually gone and created a 3D scatter plot of the data, essentially a space-time cube of that data set. So again, you can go further and chain more commands onto that. We could call set size. So whenever Maxime was setting the size in the visualization editor, underneath it was doing something like this. It was calling set size on using a particular parameter such as base, but maybe I want to use time for this. I rerun it. And then you can see it's actually set the size of the various points based on the base where that data point came from. And finally, I can call set color. So the set color example is kind of nice because it demonstrates the use of link. So I call set colors. I need to pass it in an array of colors. As you can probably see in that tiny text there, it's expecting an array of colors. So what I'm going to do is I'm going to use link to transform the time dimension into a color. And to do that, I'm going to get the data from the time dimension. I'm going to call select. So this is a link function. It's a little bit like the select statement from databases. I'm going to call select. It's going to pass in each value out of the time array, and I'm going to convert it into a gradient color. So up here, I've actually set up a little gradient which ranges between blue and red, and that has an evaluate function. So I can transform that particular data value into a color. So if I jump back to Unity, I can see now that it's colored my scatter plot using that gradient. So that's the view builder. That kind of demonstrates how you can use the Fluent interface to programmatically build up your views. And I think it's a really nice way if you want to create your own interactions or your own systems, you can actually dive down into the guts and build your own systems on top of this. It's worth noting that underlying these views is something called a big mesh, which Maxime kind of touched upon. And the big mesh is really about rendering huge amounts of data points. So as Maxime said, if you just use game objects within Unity, you're going to be looking at 10,000 data points that you could visualize. If you use just vertices out of a mesh, you're looking at 64,000 data points. But with the big mesh system that's in IATK, you can visualize hundreds of thousands to potentially millions of data points, and it'll scale well. If all you want to do is actually play with like really large amounts of data points in meshes, then you want to dig down into the big mesh. If you want to start building your views and applying styles, then look into the view builder. This code snippet I'll just pass over, but again, this is a similar sort of code, but we're actually passing in a lines type of geometry. But actually, in fact, I'll jump into this and show that I can actually change this material to spheres, for example, which I quite like. Jump into Unity, give it a run. And now I have some nicely rendered spheres instead of just points. So the framework's quite flexible. I can build my views. I could potentially build several views from the same view builder, but using different materials if I wanted to. So if you wanted to explore your data using different visualizations, that could be a way to go. Lastly, I'm going to touch upon filtering because we're going to facet this data into 4 data sets, and we're going to build some interesting interaction out of it. So the way you can facet your data is to use link. In this case, in this demonstration, which is actually in the source code, we've built up this what's called a delegate function, and this is kind of an interface for a filter function. We've created a basic filter function which takes in a data source array value dimension. It doesn't matter too much what it takes in. I just want to demonstrate the output. We are using, in this case, we're using link, so we're doing a select. We're doing a bit of munging here, and then we're selecting where a particular value equals the value we're searching for. So this is where we can start to see where link can help us filter data, because it starts to look like SQL, and you can actually use an SQL-like syntax within link using C#. So that's quite nice. And then this base array filter will convert it back to numbers. And then what we can do with that base array filter is that we can call it as a function. We pass it in our data, we pass it in the data set and the value that we want to filter on. And that lets us facet our data along a certain dimension. So if I jump back here now, and I'm going to disable this particular code that we've got running. I'll enable this one. So in the source code, there's a facet by example. I'll jump to the facet by function. What the facet by lets us do is it lets us filter on a particular attribute. So here it's going to filter on base. It looks like I think there are 4 bases in the data. So we'll actually facet that data by bases and build up a set of 4 views. So if I give that a run, so we can see there that it's faceted my data into 4 separate views using link and the view builder. So that's pretty nice. The next step that we want to do is build up a novel interaction using this faceted data. So we're going to use the faceted data that we have, and we're going to control their positions programmatically so that we can create some sort of funky accordion interaction. So I will jump back into the code. And to do that, there's not a lot to it. So this is our update function. As I said earlier, the update function gets called every frame. So that gives us a good point to create some novel interaction. What we have is we have 2 transform objects, so T0 and T1. And they're going to be used for my left and right controller. And then we have a list of the faceted views in this accordion array. So all we're going to do is we're going to linearly interpolate the position and rotation of each of those views based on how far apart and the orientation of my controllers. So to demonstrate that, I'm going to jump in here. And what I'm going to do is I'm going to pull these out first. I'm going to set the T0, which is going to be my left controller, T1, which is going to be my right controller, and just give that a run. Okay, so this is my scene. We can see these left and rights actually have a sphere on them just to help me visualize them. And I can move them back and forth, and it will do some nice interpolation. I can rotate them, and it will do a fanning effect. So that's pretty nice. So what I'm actually going to do now is I'm going to, can I see those? What I'm going to do now is I'm actually going to drop those left and rights into the hand controllers. So I can actually put it into controller left, controller right. I just want to reset those positions. And reset the position.
So now Andrew is going to play some accordion, I guess.
just pick up these controllers. And now, now what I can see is that quite simply through a few lines of code, I've actually created a novel interaction technique where I can quite fluidly inspect these 4 facets of data simultaneously. Fan it like that. Yeah, so that's quite nice. So that's just
I'm very impressed, Andrew.
That's just an overview of how you can use the underlying code to build some novel interactions and potentially some novel visualizations using the code and not just the higher level visualization class. So I think that's pretty much where we can wrap up, and maybe we can have the system running so people that are interested in playing with the visualizations in VR can have a go. But in terms of takeaways, like we said, IETK scales with the number of points to visualize, so it's really built to handle large data, and that's really a strong focus of visual analytics. Just be considerate of the number of visualizations that you're creating. So it can handle large data numbers, like large numbers of data, but if you start creating hundreds of visualizations, you're really exponentially taxing the system. For transforming your data, look at using third-party Python, R, or even just Excel to clean, order, and transform your data, because at the moment we don't have those facilities built into IETK. But if you want to add them, feel free to add them and push them back to the repo. IETK is a toolkit, and it's designed to integrate with other packages. So, a part of what Maxime demonstrated, which I think was really great, was he demonstrated taking the virtual reality toolkit, which is all about interaction, and combining that with IETK. So look into other packages such as Mapbox and Vuforia, all these sort of packages. IETK will integrate with them, and you can use them to build more complex systems. And I guess the last point is that IETK is an open source project. We don't have a team of engineers building this. At the moment, it's just us. So really, this is, we're handing this out to you guys to build upon, push it back to the repo, and really build this into a great project.
No, I think, as Andrew said, we were a bit early, but we allocated some time at the end of this tutorial. For example, some people who never tried virtual reality or virtual reality data visualization. We have a few demos. We have the IMAXIS system running. If you want to just have a look at how the interface looks like, if you want to play a little bit with it, you're most welcome to just talk to us until the break. So so I think that's it. And thank you very much for coming. It was nice to see that many people here actually. And thank you.